Well, it's a good day to you all. We are here on Yellow Physics and live. Today we'll be covering magnetic moments and looking at Ampere's law. So, as you have already done much on magnetic fields, I'm not gonna dwell much on that. So, if there is something that you might have missed going forward with what we're going to be covering today, you can visit the previous recordings that were covered in our previous sessions. So you can just check from our list of recordings, our list of videos and topics that we have covered so far. So I'll just get on to today's business, where we are covering questions 21 to 30 of this TAT. This is TAT 4, which is the set of questions that you have available for you on Moodle. So with our question 21, this one is a simple one that looks at basically we can it's basically related to Ampere's law. So it reads: a straight current carrying wire is bent into an equilateral triangle as shown below. So determine the net magnetic force on the wire. So this is to do with force actually. So it means it's an application of the right hand rule. So you can have Fleming's right hand rule, Fleming's left hand rule for the motor, which is for getting the force, or the right hand rule for the generator, where we want to find the direction of the induced current, looking at Faraday's law, which is the next thing that we'll be covering in our next sessions. So for this one, we need to find the force. So the principle by which this works is you pass a current through a conductor, then a force acts on the conductor that is in a magnetic field. So this is because of the interaction of the magnetic field due to the current inside the conductor and the magnetic field due to the external magnets, or due to the external field within which the conductor is lying. So that interaction between the two fields is such that they would cancel out on at some point where they are opposing, because they are vectors, and they would superpose and reinforce at another point where they are in the same direction. So when that happens, the side where they superpose, this field is stronger than the side where they cancel, so the force will push it towards the weaker side. Basically, that is what happens in essence. So for this question, we need to find the force overall acting on that wire. So because we've got a loop, in this case a current loop, the current is flowing from point A right through the wire back to the same point. So when that happens, it means generally the effects of the currents are cancelled out as it goes right round that closed path. And so let me see what possible answers do we have there. So we have IBL. So remember, for our force, we have to, the calculation, this formula is correct, IBL, but it says in the Z direction, so Z is in the K. So in this case, we have got the first part, which is the first diagonal line through the triangle there, the one to the left, will interact with the magnetic field, and the angle there between the field and that line will be given by a 90 minus 60, because that is the angle with which we find. So if for that perpendicular, the angle is 90 degrees, so that would be the angle. And if they are in the same sense, there's nothing like the one that's horizontal here where we have L. There is nothing that's, there's no force that's acts on that part of the conductor, because it is parallel. So it's because it's cos 90, which is 0. So in this case, what we are considering there is the angle between, let's say can we say between the perpendicular to the wire or to the conductor and the field itself. So because if we are to say for the force, okay, this is a sine. Okay, so this is given by sine. So if it's given like this, we know that we've got force equals to, what do we put there? B cross IL. So it's this IL is a vector component in the direction of the displacement, which is the direction of L. And then that is also our other vector. So this is also equivalent to BIL sine theta if we take the cross product like that. So what does that mean? If we have our field in this direction, and we know that the angle of this equilateral triangle, the angles are equal, and because it's equilateral, so they are 60 degrees each. Then when we have, yeah, so it's the angle that is between the wire itself, the conductor itself, and the field. So it's the angle between the conductor itself and the field. And in this case, if our conductor is in that direction and the field is in that direction, then our angle is still that angle theta. And in this case, the angle, because the current is flowing this way, the angle there is 180. So that angle there becomes 180 for the other current. And the angle for the other current, which is down the right side of the triangle, will be minus theta. So that's minus theta, or minus 60. So that's basically, those are basically the two angles. So with sine, so with sine 60 for this one and sine minus 60. So the total force acting on this conductor will be B, which is the same. Then I is also the same, and L, the length of the sides are the same. But the first one is sine 60. Then this next one is minus or plus sine minus 60. The other one is still BIL, because all those components or those terms are the same for all the forces on each component or on each side of the triangle. Then the other one is sine 180 plus sine 180. So these two, sine 60 plus sine minus 60 is sine 60 minus sine 60. So this is 0. And sine 180 is also 0. So this is BIL times 0. And the force is, net force is 0. So basically, that's how the calculation goes. But we would actually, even by recognition or just knowing that this is a closed loop, if current goes in a closed loop, the effects of the currents around the loop will cancel out. So the net force there will be 0. But take note, this is generally force. We're looking at general force, but we can still have torque, because the force that's on one plane, if we consider our, which rule did we say we use? The left-hand rule. So if we consider our left-hand rule, then with the field by the first finger, the current through the second finger, which is this. So you've got a field to your right, current is basically upwards, then the force will be, so did I put it? Okay, so if field current upwards, so the force will be into the plane. So if you have your field to your right with your left hand finger like this, and you have the current sort of with the component upwards, then the force is into the plane. And the other one, field is to the right, the current is kind of downwards, and the force is out of the plane. So we have a force into the plane. Let me use a different color. So if let's, okay, maybe this one. So if we have our force, the force at this point is into the plane, That is decline. So that's our force into the plane. We mark with an X. Then the force on this side is out of the plane. We mark with a dot. So overall, if we would fix this triangle or triangular loop at from its center along the axis, which is the z-axis, then it will rotate with a force that's basically giving a torque like that. So one goes into the plane, one out of the plane, and we have a torque, and a torque due to the two forces acting in opposite direction. So there's still torque for this loop, but the forces, if we are to consider the translational forces, we're just considering the loop being forced into the plane and out of the plane by equal forces, and the net force there will be 0. F net will be 0, like that. So that's basically the first part, and I'm sure we're gonna have more questions that relate to this type of discussion. So our answer there will be D. Okay, it doesn't allow me to select for whatever reason, but it's okay. We have 0 there. The answer therefore will be D. That will be the answer. Then the question that follows is question 22. So with question 22, a segment of wire carries a current of 25 amps. So we just write our data there. Is 25 amps along the x-axis from x equals to -2 to x equals to 0, and along the y-axis from y equals to 0 to y equals to 3. So a picture of what's happening there with x-axis and y-axis. So from -2 to 0, and from 0, 1, 2, 3 to 3 on the y-axis. So that's x and y. So the current is 25 amps, so we've got I flowing like that. And in this region of space, the magnetic field is equal to 40 millitesla. So we have our field, which is in the positive z direction. So if we would have our z, let's say like that, then the field is basically in that direction B. So we've got B in that same direction, parallel to the Z. Then what is the magnitude of the force on this segment of wire? So we still want the force. We still want the force that is acting on this segment of wire. So take note, the plane of the wire is perpendicular to the Z direction. It means the X direction is perpendicular to the field. The Y direction is perpendicular to the field. So F net magnetic force is equal to Fx plus Fy. That's the net force, magnitude of the force on this wire. And this is Bi times Lx sine 90 plus Bi times Ly sine 90, because the two wires are perpendicular to the field in either sense. So B and I are given. So we've got Bi, we know this. Lx is the value of the x, which is from -2 to 0. So that will be 2, and sine 90 is 1, plus Bi Ly, which is 3, plus sine 90, which is 1. So we've got 5 multiplied by B, which is 40 millitesla. So which means I would come back here. B is 40 millitesla. That's the given information. So we have 40 there, millitesla, or times 10 to the -3. And I, which we said is 25. So that's all. Let's see if we can calculate that together. We have 25 by 5 multiplied by, I'll open the bracket, 40 milli, 40 times 10 to the power minus 3, negative 3, and close bracket. Okay, so it says 5. This is 5 newtons. We have 5 newtons there, and we have 5 newtons on our solutions, which is C. So that will be a 5 Newton force acting on this segment of the wire. It will be a 5 Newton force. Okay, so I think that's it with that part. We move on. Question 23. Question 23. So with question 23, a wire having a mass per unit length of 5 grams per centimeter carries a current of 2 amps horizontally along a positive axis as shown. So there is the wire in black with the current flowing to the right along the positive x-axis. What is the direction and the magnitude of the minimum magnetic field needed to lift this wire vertically upward against gravity? So our wire carrying a current I, which is 2 amps, and the wire has got a mass per unit length of that. So which means there's gravity acting on the wire, G, and the force there is mg. So that is mu g over L times L. So the mass is actually, remember mu is equal to mass per unit length. So our mass is mu times L. So we can express our force, gravitational force, like that. Then the force that's required, the minimum magnetic force needed, FB, which should be equal to Fg, is equal to BIL. So if this magnetic force is to be minimum, then it has to be perpendicular. So the sine 90 is 1 there. And this therefore should be equal to mu times G times L. So because we've got like terms on either side, we can cancel. Then we find B is equal to mu G over I. So it's in terms of all the given quantities, where mu is 5 grams per centimeter, which is how many kgs? 5 times 10 to the minus 3 kgs per centimeter, which is per 0.01 meters, multiplied by 9.8 over I, which is 2. Okay, so we've converted the given mass per unit length, the linear mass density, into standard units, to the standard units equivalent. So that means we're 5 times 10 to the minus 3, 10, not like that, 5 times 10 to the power negative 3, divided by 9.8. So times 9.8, then divided by 0.01, which is the centimeter, and also divided by 2. So we get 2.45 there. It means B equals 2.45. The unit is the Tesla. So we've got 2.45 Teslas of the magnetic field that should keep this wire or this segment floating against gravity. So that's 2.45. Okay. 0.245. Did I miss something? 5 grams. 5 grams is 5 times 10 to the minus 3, 0.01, 9.8, and 2. Did I really get 2.45? Yes, I did. Okay, so we've got 5 grams per centimeter multiplied by G over I. 5 over 1,000 and 0 over 100. No, 1, 2, 3. That's 5 grams. Divided by times 9.8. Okay, I think I got it. Then divided by 1 centimeter is 0.01. And then it's divided by 2. Okay. Is my conversion wrong? Could my conversion be wrong? Mass per unit. Oh, the length, I removed the length is not there. It's mass per unit length. The lengths are all cancelled out. We remain with mu G over I. I think I see where this is 0.5 grams, not 5 grams. This is 0.5 grams. So it makes it easier. Then it means this becomes 0.245. Okay, sorry about that. I think that's over excitement, but it's okay. We have 0.5 grams per centimeter, the linear mass density, not 5 grams per centimeter. So that is 0.25 Tesla, and the direction is along the positive set, because the gravity is downwards. This force has to be upwards. So we have to choose D. We have to choose D. So the negative z is for gravity, negative z-axis is out, everything that says negative is out. This force has to be in the positive z, and it's not 0.5 Tesla, but 0.245. Okay, that's fine then. The next question, in the figure below, the cube is 40 centimeters on each edge, 4 straight segments of wire A, B, B, C, C, D, and DA form a closed loop that carries a current I of 5 amps in the direction shown. So from A, we go down the y-axis to B, then B to C, C to D diagonally, and D to A diagonally again. So the current is the same, but this is a closed loop. So the magnetic force on the system, the net magnetic force on this system will be 0. No need to calculate. Still a closed loop system. So whatever we do, if we multiply the field, in this case is in the positive y. So it is only the components BC, C, D, and DA that have the force acting on them. And these forces ultimately cancel each other out. So the net force becomes 0. So yeah, if you want to verify the calculation, you can do that. See the angle in this case between the wire and the conductor for CD and the field is 45. So you would deal with your sine 45 there with the sine 45 there and see what happens. Is this sine 45? This one will be, it has, can we say it has 2 components? So that one makes an angle, and this one is cutting the field perpendicular. So it has two components. One that's yeah, those two components are still perpendicular. They're still perpendicular, but one of the components cancels out the effect of CB because it has a component that is along the Z. Then the other component cancels out the effect of what? The effect of CD that is along the X. So it cancels out the X component of the CD segment. Then the other component of the CD segment is along the Y, so it doesn't have any effect. It's not affected by the field, and hence it will not have a force. So those two components, if you see the one that goes along the X from C, it is cancelled by the one that goes along the X from D to A. So overall, the effects will cancel out. No need to calculate then. So we'll go ahead and look at question 25. So for question 24, we have 0. Question 25. So you can show with the calculations anyway and show that the BIL sine theta for each segment gives 0 at the end. So ideally, if given an exam questions, then you need to show it's 0. It's not just a matter of putting the answer there. So the current loop is oriented in 3 different positions relative to a uniform magnetic field. In position 1, the plane of the loop is perpendicular to the field lines. So the whole plane perpendicular. In position 2 and 3, the plane of the loop is perpendicular to the field as shown. The torque on the loop is maximum in which case? So in the first case, which is position 1, you have your field. So that's the field, and we have a loop. Like that. And the field is passing through that loop perpendicular to it. So it will be perpendicular to the loop. So the force that acts on each segment in this case results in a current loop oriented in 3 different positions. So if we have we assume a current moving like that, then what it means is for one part of the segment, we still apply our the same rules. So we have a force. We'll look for a different color. Okay. So we have a force from the top part of the loop, which is in this case field, current, and the force is downwards. So with the field and current most likely into the plane, the force is a downward force. So we have F1 there. Then automatically this is a force upwards, F2. And the same applies for the field and the current going up. The force is towards, that's F3 and F4. So if you look at it, there's no torque there. It's just the forces acting on that conductor in that sense. So the torque can't be maximum in that sense. But for 2 and 3, the elements, so if we have our field like that, and one of the conductors, the loop is in that sense. So the sense for 2 and 3 will be the same, because it is just a matter of taking that same conductor and having it lie horizontally. So if we have our current around the loop like that, and the magnetic field in that direction, then field, current, force into the plane. So the first force is into the plane, that's force, and this side the force is out of the plane. So already that's giving us a turning effect or a moment about the axis of the conductor. The components at the top and at the bottom will have no force, because they are parallel to the field. So we have a force or a torque for this case, and we also have a torque for the case indicated by diagram number 3 in the same sense, from the two sides that are opposite and perpendicular to the field. So that's where we have maximum torque, and according to the solutions here, it's only positions 2 and 3. So our answer is E, positions 2 and 3. Okay, so that leads us to question 26. Question 26. If you have a question, you're free to just ask the question. You can type something on the chat box, then we'll be able, or just unmute your mic if you are connected to Teams, then we'll pick it up from there. Otherwise, so we proceed to question 26. Another circular loop, radius 5 meters, carries a current of 3 amps and has a unit normal vector 2I minus j plus 2k. The question goes, what is the magnitude of torque on this loop when it is placed in a uniform magnetic field of value I minus 2j Tesla, and ij and k are unit vectors. So we know our torque is given by IA, which is the current area component, which is a vector component of the current and area cross time B. So it is the cross product between IA and B, where A is given as a vector normal to the plane of the loop. So it's actually an areal vector. So with that in mind, it means we've got IA or BIA sine theta for our magnitude, the magnitude of the torque. Otherwise, for the direction, it's perpendicular to both the normal to the area, to the plane of the loop, and the magnetic field itself. So the plane made by the normal to the loop and the magnetic field will give us the perpendicular direction to it gives us the direction of the torque. So that's basically another vector. So in this case, to get this cross product and get the magnitude of the torque, we can we don't know what theta is, so to just avoid this route, we just go the cross product, where we have IA cross B being equal to the magnitude of I, J, K of I times A. So what is I times A? I is given to be 3 amps. So IA equals to 3 amps times the area is pi r squared, times the unit vector of the giving the direction of this area, which is 2I minus j times 2I minus j plus 2k. So with the r squared being 0, 0.5, so we've got 0, 0.25 times 3, 0, 0.5 squared is 0, 0.25. So we've got 0, 0.75 pi multiplied by 2 minus 1, 2. So that's basically our vector form of IA. So that's 3/4 pi. So we can say 3 over 4, 3 pi over 4 multiplied by 2, or 0, 0.75 by 2, that's 1,5. So that makes it 3 over 2, 3 over 2 pi, and minus 3 over 4 pi, and the same, and 3 over 2, 3 pi over 2. So that's for our IA. Then for B, we're told B is 1 minus 2j, so we've got 1 minus 2 and 0. Then we take the determinant of this cross product. So the first thing we can so we'll block the I, and we deal with the determinant of this quadrant, the bigger quadrant, which is these as our components A, B, C, D. So which means for the I direction, we've got the determinant of AD minus BC, which is 0, minus 3 pi over 2, and minus 2 will give us minus 3 pi. That's for the I. Plus for the J. For the J, what do? We block out the J, which means this part is out, and we get the determinant for this is our A, that is our B, this is our C, and that is our D. So AD is 3 pi over 2 minus BC, which is minus 0. So that's the 3 pi over 2 for the J. So for the J, we only we just eliminate or forget about this part, which is within the blue lines. For the first part, we had to leave this part, which is within the red circle. So now for K, we'll block out this and our A, B. This is our A, B, C, and D. So which means this is plus K, unit vector. AD will be 3 pi over 2 times minus 2, which is minus 3 pi. Then minus 3 pi over 4 times 1, which is minus 3 pi over 4. We are done. So this is 3 pi I plus 3 pi over 2 J, then minus 3 pi plus 3 pi over 4. So this actually makes a plus. It gives us 2.25 pi. So this is 12 over 4 minus 12 over 4 plus 3 over 4, which is minus 9 over 4. Minus 9 over 4 pi. So this is our torque and its direction. This is the torque in vector form. And we want the magnitude. The magnitude of this torque will be the root of 3 pi squared plus 3 pi over 2 squared plus minus 9 pi over 4 squared. So that expression there would give us Calculator. So we have the root of, open bracket, 3 pi squared, close bracket, square, plus 3 over 2 pi squared, which is 1.5 pi, close bracket, and squared, plus, open bracket, negative 2.25, negative 2.25 pi, close bracket, and squared. That gives us 12.69 Newton meters. So this is the value of the magnitude of the torque. That's the value of the magnitude of the torque, which is D. We have that answer there given as D. So that's how we get the torque. It's quite an easy and interesting process. You just need to express your vectors. Remember, the the cross product is non-commutative. So it's is it commutative? Yeah, it's non-commutative, meaning this is not equal to B cross IA. So it's not equal to that. So if B cross IA is negative, it will give us a negative value of that. So which means if you start with a B there, you have 1, -2, and 0 at the top, and you have the IA down. But then B cross IA is something else. It gives us a torque in a different direction, or some other vector in a different direction. So in this case, for the torque that we want, we have to do IA cross B. Then we get the torque, and it's a correct direction. Okay. Then the next question is question 27. The figure below shows the orientation of a rectangular loop consisting of 80 closely wrapped turns, each carrying a current I. The magnetic field in the region is 40 millitesla in the direction X, and the loop can turn about the Y-axis. If theta is 30 degrees, A 40, 0.4 meters, and B 0.3 meters, I 8 amps. What is the magnitude of the torque exerted on the loop? Okay, so that's an interesting one. We have our axis like that. Then a loop of wire at an angle theta to the X, Z, Y. And therefore there are 80 turns. The one side has got a size A, the other side has got a size B. Then the current is flowing right around the loop is I. So the same thing will apply for us to get torque. We want the magnitude. So we know theta. So we say BIA sine theta. So what is theta? What is theta in this case? Theta is the angle between the normal to the area, and let's see, sine theta. We have our current. There is an angle between the current and the direction of the field. So our B field is, let me use blue. Our B field is along the X like that. So the current is making an angle theta with the B field. Then we have, so we have the current, we have the field, and that torque be the turning effect perpendicular to both the current and the field. Okay. In this case, if theta is 30 degrees, what is the magnitude of the torque exerted on the loop? So yeah, it's still okay. So it means in this case, our area, the area is the shaded region. We can shade it in black. And the normal to the area in this case, normal to the area points in that direction, which makes it perpendicular. It makes it perpendicular to the current like that. And so if this angle is theta, then the angle in which the area vector makes with the field is 90 minus theta, to be 90 minus theta. So which means in this case we have sine, we can call it sine phi, the angle in which the area vector makes with the field. So what does that mean? We have B is given 40 millitesla multiplied by I, which is 8, multiplied by A, which is 0.4 times 0.3, then multiplied by sine. What is theta? Theta is 30 degrees, so the sine 90 minus 30 is sine 60. So that should give us the torque. That should give us the torque. So if we can check with the calculator what that torque will be, 40 milli times 10 to the negative 3 multiplied by 8 multiplied by 0.4 by 0.3 and multiplied by sine 60. So 0.033. Oh, we also have n there. So because we have n tens, this torque will be proportional to the number of tens. So we multiply everything by 80. So we still have multiplied by 80. 2.66. So 2.67 is Newton meters becomes our 2.67 or 2.7 Newton meters is the magnitude of that torque. So we're given the angle there. If you check, let's see, I'm sure that would be a distractor. If we use instead of 60, we resort to 30. We've got 1.536. I'm sure they would put 1.5 there. Yeah. So already you have to know what your angle theta should be based on. So in this case, the theta is the angle that is lying between the aerial vector and between the aerial vector and the magnetic field. So our theta should be the angle normal to the loop. So the same we have a similar question here with theta given, where the figure shows the orientation of a flat circular loop consisting of 50 closely wrapped turns, each carrying a current I. So the magnetic field in the region is directed in the positive Z direction. So we've shifted the magnetic field from, in this case, from this x-axis in the previous case to the z-axis. That's the only difference. So the loop can turn about the y-axis as it was doing in the previous, but theta is 20 degrees, the angle made between the orientation of the current or the orientation of the plane of the loop and the x-axis. And R is 0.5 meters, I is 12 amps. What is the magnitude of the torque exerted on the loop? So we said magnitude of torque is N times B times I times A times sine of theta. Or let's call it phi, so that we know we have to look at the angle between the normal to the plane and the field. So in this case, N is 50, B is 50 times 10 to the minus 3, I 12, A is pi r squared, pi times 0.5 squared, and sine of the angle. What is that angle now? This time around, we have a field that is down in the Z direction, and our loop is oriented at an angle theta to the x-axis. So that means the normal to the loop will be oriented as well at an angle theta to the z-axis. The angle there will be theta. So how does that work? If this is the normal, then this normal makes it an angle. So if that is theta, this so initially that so you can think of it this way: if the loop lies along the x-axis, then its normal is parallel to the z-axis. When we shift the loop about the y-axis and we shift it an angle theta towards the z, then its normal also shifts. Let me read through this. So initially the normal will have been lying along the z. So if that is our z, something like that, I think it's straight. So initially that's the direction in which the normal will be lying, but by tilting the loop an angle theta from the x, then also the normal will shift an angle theta like that. So it makes an angle theta such that this angle here that remains is 90 minus theta. So remember that angle, the angle between this line and the minus z or z prime there and x is 90 degrees. So that angle was 90 degrees. So we tilt the normal to an angle theta, then that normal makes an angle 90 minus theta with the x. It makes an angle 90 minus theta with the x. So it still makes sense because this normal and the new orientation of the plane of the loop will be 90 minus theta plus theta. So that angle is still 90 degrees, which is the angle between the normal to the area and the line of the current. So which means that angle is theta. So that means the same angle that we consider there is still the same theta that's given, which is the 20 degrees. So we have sine 20 here. And therefore, doing the calculation will give us, we can say we have, in this case, 50 multiplied by 50 milli Tesla times 10 to the power of -3 then multiplied by 12 multiplied by pi times 0.25, which is 0.5 squared. So I didn't put 0.5 squared there, I've already calculated that. Then sine 20. 8.05. So we've got 8.05, which is 8.1 for this one. So the value is 8.1 Newton meters. So our torque is 8.1 Newton Nm, Newton meters. So that's basically what is important there, to know the value of your theta, which enables you to calculate the torque. So if I've just entered theta equals to 20 there. With theta equals to 20, you do get the 22, and so with multiple choice questions, you still find all those possible solutions are still given. Okay. So the next question. Our next question there is question number 29. A velocity selector uses a fixed electric field of magnitude E, and the magnetic field is varied to select particles of various energies. If a magnetic field of magnitude B is used to select a particle of certain energy and mass, what magnitude of magnetic field is needed to select a particle of equal mass but twice the energy? So with a velocity selector, we can have crossed fields where we know that the velocity of the particles that go through undeviated can be given by E over B. So this is when the magnetic force is equal to the electric force. Then we know the magnetic force is B, Q, V, and the electric force is Q, E. Then for this charge with particle with charge Q, it means V will be equal to E over B. This is the velocity of particles that can go through the crossed fields undeviated. Okay, so the velocity selector, what it does is applying we use the force that particles that are charged and they have different masses, so they have a different charge to mass ratio, right? So it will act on the charge of a certain mass and give it by giving it a certain force, and that force will, in this case in a magnetic field, allow it to describe a kind of a parabolic or circular path, and from the point of a certain radius r, we'll be able to collect particles of a certain charge to mass ratio. So with those particles, we know particles of the same charge to mass ratio will be collected or will emanate from an outlet of radius r from the point of entry into the field. So this r is basically given by mv squared. So we know that we've got the magnetic field giving this a centripetal, we call it a centripetal force. So mv squared over r will be equal to bqv. then that means we can make our R the subject with mv squared over b q v equals to R. And we remove the R there, the v's, then mv over bq equals to the R. So already you can see the m over q there, the b will be constant. The velocity of the particles, they are already accelerated to a certain, by a certain potential through a certain through a certain potential to a velocity v, such that particles that are of the same charge will go through that potential. They are given kinetic energy, and that kinetic energy gives them this this velocity. And so that charge to mass ratio will always be collected from a radius r. So if we can talk of maybe a field like this for our velocity selector, b is into the plane. Then we've got particles, let's say they are electrons, which come into the field from that point, electrons. Then this beam of electrons, because they are negatively charged, the current is opposite. We want to find force. Field is into the plane. Then from the point of entry, the current is opposite the flow of electrons. They experience a force towards my right. So we've got field into the plane, current downwards, and the force is to the right. So from the moment they enter, they would experience a force to the right, and this force results in something like that. So this is the path the electrons will follow, and from that point, this is the radius that we are saying we calculate. So at this point, we exit particles of a certain charge to mass ratio. So if it's electrons, it's the electron charge over the mass of electrons. Otherwise, if there are other particles, then it is only particles of this charge to mass ratio that will emanate from that point with a certain velocity. So this is basically the basis of our velocity selector. So this part of the question says if B is used to select a particle of certain energy, so certain energy meaning mv squared, half mv squared kinetic energy, and mass, then the magnitude of the magnetic field that is needed to select a particle of equal mass but twice the energy will be. So if we want particles of twice the energy, then it means we've got we're saying in this case B is equal to RQ over MV. So if the mass is to be the same but the energy is to be twice, what would that mean? Same mass, twice the energy. A velocity selector uses a fixed electric field and of magnitude E, and the magnetic field is varied to select particles of various energies. If a magnetic field of magnitude B is used to select a particle of certain energy and mass, what magnitude of the magnetic field is needed to select a particle of same mass but twice the energy? So if we were to have same mass and twice the energy, it means the velocity is the new velocity, V new is equal to √2 of V old, such that V new squared is equals to 2V squared. So with 2V squared in the picture, That is the one that gives us twice the energy. Then we said we use this one to say V equals to E over B. So if E is constant and we have root 2V there, I think that makes it B over root 2. Okay. So we have a fixed electric field, magnetic field varied to select particles of various energies. If the magnetic field of magnitude B is used to select a particle of a certain energy, meaning a particle of certain velocity, mass and Q would not change. So we use B to select particles of a velocity V. So if we were to select particles of a velocity root 2V, then the value of B should be root 2B. There are two things here. If V knew to V to B equals to E over V. Root 2V B mu B times root 2 equals to E over V. Okay, so I think I said, let's see if this works. So we're saying I just want to use two approaches there, which I've contemplating on using. So if we say our V, according to that first equation, V equals to E over B, our new velocity, V primer, will be equal to E over B primer because E is not changing. And this V primer is root 2V, which is equal to E over B primer. So making B primer the subject, B primer equals to E over, okay, root 2 times B primer equals to E over V, where E over V is simply B, which is equal to B. So the new B is equal to B over root 2. That's what it means according to that, which will be equal to B over 1,4. 1 over root 2 should be 0,7. So this one gives us 0,71B. That's for the new B with that considering the crossed fields. Then considering this expression, if we consider that expression, we are going to say, in this case, mv over r q equals to b. So if we have a velocity v with a magnetic field b, our velocity will be v, meaning we've got a kinetic energy, which is the initial. Then for the new kinetic energy, which is twice, the mass is the same, but the v is root 2 v over. So we want to select particles of equal mass but twice the energy. So this is twice the energy, and our radius is r with the q there. So it is twice the energy because of the velocity, which is the new velocity. And this is our b primer. So with this one, mv over rq, mv over rq is the old b, so it gives us root 2 of the old b equals to the new b, which is saying 1,4 b. Okay, so there are two things. Is it b over root b, or is it b over root 2 or b times root 2? Is it b over root 2 or b times root 2? Because the other one is 1,4b, the other one is 0,71b. So it's between those two. What we need to understand with this question is the nature of this velocity selector and how the electric field, are we dealing with the crossed fields, or the electric field is there to accelerate the particles first, which gives them like a constant, is it like a constant? Yeah, it will give particles of a certain charge for the same mass, particles of a certain charge, some kinetic energy. Then the magnetic field is responsible for the selection, which is the part where we have the centripetal force making the particles define or describe a parabolic path, or that kind of semicircular path to be selected out through a certain output point. So otherwise it would mean, I'm thinking, if this is the velocity selector where the fields are not crossed, fixed electric field magnet, sorry, to, yeah. So within the crossed fields, we have basically the electric field giving a force in one direction and the magnetic field giving the force in the other. So for crossed fields, it will be two plates. Our electric field, let's say that's the electric field E. So that ideally makes it positive and negative this side. Then if we have if we are to have a magnetic field that gives us a force upwards, then it means in this case we are inputting our charge first finger field and the current, or yeah, it can be, we can have our magnetic field so if we have our a magnetic field in this direction, yeah, if the magnetic field is to be to the, is it to the left? Yeah, the magnetic field can be into the plane, so B can be into the plane. That's B. The X means B is into the plane. So basically that would be our B. And then if we have a current, meaning if let's say we have positive charges, like an alpha particle moving in like that, or if it is electrons, then those electrons should be moving in the opposite directions. So in this case, it's positive charges moving into the field to the right. Then the positive charge tends to follow the electric field, so it experiences a Fe. So that Fe is downwards on the charge because it follows the field. But the magnetic field, using that same rule, magnetic field current to the right, the force is upwards. So we also have Fb upwards. So this is where we have also Fb, which is upwards. So the moment the two are equal, then the particle goes through undeviated. Then if we are keeping a constant Fe and varying Fb, then for selecting particles, it means Fb will allow us the particles to describe a path like this. Then we select those particles out from there. So this is the particle of a certain charge and mass, and they are giving a certain velocity. They have a certain velocity with which they exit. So this is the basis of this question, and why I had to describe the two ways in which the velocity selection can be made. So in other words, we can think of it in this case as one where we have crossed fields, because we're talking of the E and the B field together being used in sync or simultaneously. Whereas in this case, it's basically the magnetic field. The electric field is only used in accelerating particles out there. So it will be like a kilovolt potential to accelerate particles, and it's only the magnetic field. So which means for our case, we're going to consider this, which we calculated first, where we have 0.71b based on the two crossed fields. So we'll use 0.71b for the two crossed fields, which makes E our most appropriate answer. The final question for the day, a rectangular loop of wire has dimensions 0.5 by 0.3, and the loop lies in the XY plane as shown in the figure below. A uniform magnetic field of 1.5 Tesla is directed along the x-axis parallel to the plane of the loop. The loop carries a current of 0.9 amps in the direction shown. Based on this scenario, ignoring gravitational force, answer the following. What is the direction of the magnetic force exerted on the segment AB? So the segment AB has got a current upwards with the field going, so it's into the plane, which is in the negative Z direction. So that would be negative Z for our choices there. You'll check on the drop down on the choices, there should be negative Z. Then for the direction for BC, it's parallel to B. So there's 0. There's no magnetic force there. The direction of the magnetic force exerted on CD is in the positive Z direction, opposite to the first. The direction of the magnetic force exerted on segment DA is 0 again. Then from the point of view of the figure shown, once the loop is released from rest at the position shown, will it rotate clockwise or counterclockwise around the axis? So because it has two components, one into the plane and the other one out of the plane, the loop will rotate, in this case about the y-axis, in a clockwise direction. So that's it will rotate clockwise. around the y-axis. And what is the net torque on this loop? What is the net torque on this loop? So we have to calculate that net torque using the same IA. So it's just 110 torque equals to IA cross B multiplied by B and sine theta, which is the current given there is 0.9. So you have 0.9 multiplied by the area 0.5 multiplied by 0.3. Then B is 1.5 Tesla, and sine the angle in this case is 90. So that calculation should give us 0.9 multiplied by 0.15 multiplied by 1.5. That's 0.203. So we have 0.203 Tesla, no, Newton meters, sorry, Newton meters. That's the value of the torque. That's the value of the torque. So I think that's it for the day. You can join us again later in the afternoon. We'll be continuing with the next charts, which are related to what you covered in the lectures in the previous week. So from me here at Yebo Physics, we wish you all the best as you go through your studies. If you have any questions, please feel free to contact us. We'll be ready and happy to assist you at the earliest that we can. Otherwise, have a good day. Bye-bye.